There is a number that describes your relationship with the sun, and almost nobody has been told it. The number is 20. For every particle of sunlight that lands on you, roughly 20 particles of light leave the Earth and go out into the dark. 20 out for 1 in. And here is the part that should stop you. The energy leaving is exactly equal to the energy arriving. The books balance perfectly. The planet keeps none of it. Which raises a question almost nobody thinks to ask. If the Earth gives back every unit of energy the sun sends, then what has the sun actually been giving us for 4.5 billion years? What are we living on? Tonight you will find out. And you will find out that the universe is running out of it, and that nothing can be done to stop that. By the end you will know exactly why. Get comfortable. If you enjoy discovering that the most ordinary thing in your life has a stranger explanation than the one you were handed, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of tonight, sunlight on your skin will not mean what it meant this morning. Now, let's gently drift into this. Somewhere in your home there is a battery that has gone flat. Maybe it is in a remote control you stopped using, or a torch in a drawer, or a smoke alarm that started chirping at 3 in the morning last winter and has been silent ever since. You know what happened to it. It ran out. The energy that was in it got used up, and now there is none left, and that is why the thing it was powering no longer works. That explanation is one of the most reasonable sounding things a person can believe, and it is wrong in a way that turns out to matter enormously. The energy that was in that battery is still here. Not most of it. Not a residue of it. All of it. Every single unit of energy that was stored in the chemical bonds inside that cell when it came off the production line is still present in the universe right now. This second, undiminished and unaltered in quantity. None of it was consumed. None of it was destroyed. Nothing about the total went down. This is not a technicality or a clever way of speaking. It is one of the most thoroughly tested statements in all of science. It is called the first law of thermodynamics, and what it says is that energy cannot be created and cannot be destroyed. It can move, it can change form. Chemical energy can become electrical energy, which can become light and heat. But the total never changes. Not in a battery, not in a star, not in a galaxy, not in the whole universe. If you could add up every unit of energy in existence today and compare it to the total at any earlier moment in cosmic history, you would get the same number. So here is the question that this whole video is going to be about, and I want you to sit with how strange it is before we go anywhere near an answer. If no energy is ever lost, then what exactly is running out? Because something clearly is. The battery stopped working, stars burn out, bodies get tired and eventually stop, machines wind down, hot coffee goes cold, and never, not once in the history of the world, has a cold cup of coffee spontaneously warmed itself back up by drawing heat out of the room. Everything around you, everywhere, all the time is running in one direction and refusing to run in the other. Something is being spent, and yet the books say nothing is missing. Both of those things are true at the same time. The accountancy of the universe is exact, nothing has gone missing, and simultaneously the universe is running out of something and will not stop running out of it, and there is nothing anybody can do about that. Tonight I want to show you what that something is, and I want to be honest with you about where this is going, because the answer changes the shape of the problem rather than solving it. When you understand what is actually being depleted, you will not come away thinking we simply need to look harder for more of it. You will come away understanding why looking harder is not a thing that can help. There is a question folded inside all of this that people have been asking since the 1850s, and it is the obvious one. Can it be stopped? Is there a way around it? A loophole? A clever arrangement? A machine somebody has not thought of yet? People have tried. Some very serious people have tried, and some of the attempts were beautiful, and one of them looked like it worked for about 60 years. By the end of tonight you will know exactly why every one of them failed, and you will know that they all failed for the same single reason. But I am going to hold that reason back for a while, because it only means anything once you can see the shape of what you are up against. Let us start with what you already know, and then find the crack in it. You know that energy comes in different forms. The energy in petrol is chemical. The energy in a stretched spring is mechanical. The energy in sunlight is electromagnetic. The energy in a hot object is the jostling motion of its atoms. These are genuinely different arrangements, and one of the great achievements of the 19th century was working out the exchange rates between them. showing that a certain amount of falling weight could produce a precisely predictable amount of warmth, and that the ledger always balanced. What you may not know is that these forms are not equal. They are worth different amounts, and not in a poetic sense. In a strict, measurable, engineering sense, some forms of energy will let you do more than others, even when the quantity is identical. Take 100 units of energy in the form of electricity running through a wire. With that, you can turn a motor, lift a weight, run a computer, drive a pump, produce light, and do almost anything you want. Now take 100 units of energy in the form of warmth spread evenly through a room at a comfortable temperature. It is the same quantity. The ledger cannot tell them apart, and with it, you can do essentially nothing at all. You cannot run a motor off a lukewarm room. You cannot lift anything. You cannot light a bulb. The energy is right there, in the same amount, and it will not work for you. That difference between energy that can do things and energy that cannot is the whole story. It has a name, and it is not the same thing as energy, and that distinction is the single most important idea in this entire video. The physicists call it free energy, which is an unfortunate name because it sounds like it means energy that is free of charge, and it means almost the opposite. Free in this context means available, unbound, able to be spent. It is the portion of a system's energy that can actually be converted into work, and it is a smaller number than the total, and here is the part that matters more than anything else I will say tonight. Energy is conserved. Free energy is not. The total stays fixed forever. The usable fraction only ever goes down. Every time anything happens anywhere in the universe, some quantity of energy that could have done something is converted into energy that cannot, and there is no known process anywhere in physics that runs the other way and converts it back for free. That is what is running out, not energy, the capacity of energy to do anything. Now I want to head off the natural response to that, because it is the response almost everyone has, and it is where the real strangeness lives. The natural response is to picture a supply, a tank, a reservoir, a stockpile of good, usable, high-quality energy that started full at the beginning of the universe and has been draining ever since. Under that picture, the problem is a shortage, and shortages are a familiar kind of problem. You look for more, you find new deposits, you get better at extraction, you recycle. But that picture is wrong, and the way in which it is wrong is the thing I most want you to take away from tonight. Usable energy is not a substance. It is not a kind of stuff that exists in some places and not others. You cannot point to a region of space and say, there, that is where some of it is stored. Usable energy is a relationship. It is a difference between two things, and you cannot run out of a difference the way you run out of a substance, because a difference is not the sort of thing you can go and find more of. Think about what it actually takes to get work out of anything. A water wheel does not turn because there is water. It turns because there is water higher up and water lower down, and the wheel sits in the gap. Put the wheel in a perfectly still lake, with the same total quantity of water all around it, and it will sit there forever doing nothing. The water has not gone anywhere. The height difference has. A steam engine does not run because there is heat. It runs because there is a hot boiler and a cold condenser, and it sits in the gap between them. Heat the condenser to exactly the temperature of the boiler and the engine stops, immediately and permanently, with just as much heat present as before. Not less heat, the same heat, no gap. A battery does not power anything because it contains energy. It powers things because it contains a chemical imbalance, a separation between two states that would rather be one state, and the current flows while that separation is being erased. When the battery is flat, the energy is still in there. What has gone is the difference. Every single machine, every engine, every living cell, every process that has ever done anything anywhere in the universe works the same way. It finds a difference, and it stands in the middle of it, and it takes a cut as the difference collapses, which means that the end state, when you follow this all the way out, is not an empty universe. That is the mistake almost everyone makes when they first hear about this, and it makes the whole thing sound much more familiar and much less strange than it is. The end state is not darkness because the fuel ran out. The end state is a universe absolutely full of energy, every joule of it still present and accounted for exactly as the first law demands, spread perfectly evenly, at one uniform temperature, with nothing anywhere that differs from anything else. A universe with everything still in it, and nothing left to happen. I want to sit on that for a second, because it is genuinely difficult to hold in your head, and it is the destination of this entire story. Not a universe that has been drained, a universe that has been flattened. All the energy, none of the difference, total wealth, perfectly distributed, and therefore no transactions possible ever again. There is a word for the thing that measures how far along that flattening has got, and it is a word you have almost certainly heard and probably been told the wrong definition of. The word is entropy. And in the second half of tonight, we are going to take that word apart carefully, because when you understand what it actually measures, this whole story stops being frightening in the way you expect and becomes something considerably stranger. But that word did not exist until 1865. Somebody had to invent it, because there was no name for the thing that was increasing, and the reason there was no name is that for most of human history, nobody had noticed that anything was increasing at all. The person who first caught the scent of it was not an astronomer, and he was not thinking about the universe, and he would have been baffled by the suggestion that his work had anything to do with the fate of everything that exists. He was a young French military engineer, and he was annoyed about steam engines. His name was Sadi Carnot, and in 1824 he published a small book with a title that sounds like poetry and was meant as engineering. Reflections on the Motive Power of Fire. He was 28 years old. His father had been a general and a mathematician under Napoleon, one of the organisers of the French revolutionary armies, and had named his son after a medieval Persian poet. The younger Carnot had been trained as a military engineer at a time when France had recently lost a war, and was, in the way of countries that have recently lost wars, thinking hard about why the other side had been better at things. One of the things the other side had been better at was steam engines. British engines were more efficient than French ones. They got more work out of the same coal. And the frustrating thing, from the French perspective, was that nobody could explain why, in any principled way, engine design was a craft. You made improvements by trying things. Some worked, some did not, and the men who built the best engines could not tell you what general rule they were following, because there was not one. Carnot decided to find the rule, not a better engine, a rule. He wanted to know the answer to a question nobody had thought to ask properly, which was this: given a source of heat, what is the absolute maximum amount of work that any machine could ever extract from it? Not the best machine anyone had built. The best machine anyone could ever build, including machines nobody had invented yet, made of materials nobody had discovered, designed by engineers not yet born. That is an unusual question to ask in 1824, and the answer he got is one of the most remarkable results in the history of science, partly because of what it says and partly because of what it does not depend on. What Carnot found was that the maximum efficiency of any heat engine depends on exactly two things: the temperature of the hot source and the temperature of the cold sink. That is all. It does not depend on what the engine is made of. It does not depend on whether the working substance is steam or air or alcohol or something not yet imagined. It does not depend on the cleverness of the design, the precision of the machining, the skill of the operator, or the amount of money spent. Two temperatures, and from them a hard ceiling that nothing can exceed. Sit with how strange that is. He was making a claim about every machine that would ever exist, including all the ones that had not been thought of, and he was right. 2 centuries later, with materials science and computational design and everything else the modern world has produced, nobody has beaten Carnot's ceiling, and nobody ever will, and we now understand that the reason is not that we are not clever enough. The formula is simple enough to say out loud. The maximum fraction of heat you can convert into work is 1 minus the cold temperature divided by the hot temperature, using absolute temperatures. And when you look at that expression, you can see the entire future of this video hiding in it. Notice what makes the efficiency high. Not a large amount of heat, a large temperature gap. If your hot source and your cold sink are close together in temperature, the ratio approaches 1, and 1 minus 1 is 0, and you get no work at all no matter how much heat is flowing through the machine. You could have a boiler containing enough heat to power a city, and if the surroundings are at the same temperature as the boiler, you get nothing. Not a little. Nothing. This is the water wheel again, in the language of temperature. What the engine is standing in the middle of is not a supply of heat. It is a difference between two temperatures. The heat is what flows through. The difference is what gets spent. And here is the part that turns an engineering result into something much larger. When the engine has run, the heat has not disappeared. It has moved from the hot side to the cold side. The total is unchanged, but the gap has narrowed. The hot side is slightly cooler, the cold side is slightly warmer, and the engine's ability to do work in future has decreased permanently by exactly the amount corresponding to that narrowing, and there is no way to run the engine backwards and restore the gap without spending a bigger gap somewhere else to do it. Nature charges a fee on every transaction, and the bill always comes. That sentence is going to come back tonight. Hold on to it, because it starts as an engineering complaint about machinery, and it is going to end up somewhere you would not expect. Carnot did not fully understand his own result, and it is worth being honest about that rather than making him a prophet. He was working with the caloric theory, the idea that heat was a weightless fluid that flowed from hot bodies to cold ones and was itself conserved. That theory is wrong. Heat is not a fluid. It is the disordered motion of matter. Carnot got the right answer partly by good instinct and partly by an accident of the mathematics, because the caloric picture and the correct picture happened to give the same result for the specific question he was asking. He did begin to suspect it. In private notes found much later, unpublished during his lifetime, he had started working towards the idea that heat was motion, and had even estimated a conversion factor between work and heat that was reasonably close to the modern value. He was going somewhere. He did not get there. In 1832, at the age of 36, Sadi Carnot caught cholera during an epidemic in Paris and died within days. And because cholera was believed to spread through the possessions of the infected, his belongings were burned, his books, his papers, his notes. Almost all of his unpublished work went into the fire, and the small fraction of it that survives does so because his brother had kept a few pages separately. The book itself very nearly vanished as well. Reflections on the motive power of fire sold poorly and was largely ignored. It might have been forgotten completely if a French engineer named Émile Clapeyron had not come across it a decade later and rewritten Carnot's argument in a more mathematical form, which is how it eventually reached the two men who would understand what it really meant. I find something worth pausing on in that. The first person to notice that the universe charges a fee on everything died at 36, and the invoice for his own life was presented without ceremony, and most of what he thought went up in smoke as a public health measure. The rule he found does not make exceptions for the people who find it. So by the middle of the 1840s, the situation was this. There was a result sitting in the literature that said something absolute about the limits of every possible machine. It was correct. It was derived from a theory of heat that was wrong, and it implied, though nobody had yet said this out loud, that something in nature is used up by every process and cannot be recovered. Nobody had a name for the thing being used up. Nobody had noticed that it needed one. And the men who would eventually give it a name were, at that moment, both in their 20s, one of them a German mathematical physicist who would spend 15 years circling this problem before he found the right word for it, and the other a Scottish prodigy who would look at the same result and immediately do something that nobody expected. He would point it at the sky. William Thomson was 22 years old when he became a professor at Glasgow, which tells you most of what you need to know about him. He had published his first scientific paper at 16. He would eventually be made a peer and take the name Lord Kelvin, and the absolute temperature scale would be named after him, and he would spend the second half of his career being spectacularly right about a great many things and memorably wrong about several others. In the late 1840s, he came across Carnot's argument through Clapeyron's rewriting of it, and he did something with it that Carnot had not done and that nobody had asked for. In April of 1852, Thomson published a short paper in the Proceedings of the Royal Society of Edinburgh. It is only a few pages long. Its title is The Thing I Want You to Hear, because the title is where the whole shift happens, on a universal tendency in nature to the dissipation of mechanical energy. Read that again and pay attention to the first word. Universal, not a tendency in steam engines, not a tendency in machinery or in industrial processes, or in the specific circumstances of a boiler and a condenser. A universal tendency in nature, everywhere, always, in everything. What Thomson had realized is that Carnot's ceiling was not a fact about engines at all. Engines were just where it had been noticed first, because engines are where humans go looking for efficiency, and therefore where humans first bump into a limit. But the limit was not a property of the machine. It was a property of heat, and heat is everywhere. Every process in the universe that involves temperature, which is every process in the universe, is subject to it. And Thomson stated the consequence directly. Energy, he said, is constantly being dissipated. It is being spread out, degraded, moved from concentrated forms into diffuse warmth. And critically, He wrote that this dissipation is irrecoverable, not difficult to recover, not expensive to recover, irrecoverable by any process whatsoever, at least by any means available to material beings. That is a much larger claim than anything Carnot made, and Thomson understood it as such. In the same paper, he drew out what it means for the world in general, and he wrote that within a finite period of time to come, the Earth must be unfit for the habitation of man as at present constituted, unless operations have been or are to be performed, which are impossible under the laws to which the known operations going on at present in the material world are subject. That is 19th century prose, and it is worth unpacking rather than admiring. What he is saying is, this ends, the ending is scheduled, and the only way out would require the laws of physics to be different than they are. 2 years later, in Königsberg, in February of 1854, a German physician and physicist named Hermann von Helmholtz gave a public lecture with the title On the Interaction of Natural Forces, and he took Thomson's tendency and stretched it as far as it will go. Helmholtz is one of those figures who is difficult to summarize because he did too many things. He was trained as an army surgeon. He worked out how fast a nerve impulse travels, at a time when respectable opinion held that the speed was either infinite or unmeasurable. He invented the ophthalmoscope, which is the instrument every optician still uses to look into the back of your eye. He wrote the definitive 19th century work on the physiology of hearing and another on vision. He also gave one of the first clear general statements of the conservation of energy. So when Helmholtz stood up in Königsberg and said what he said, he was not a doom-monger or a mystic. He was the man who had helped establish that energy is never lost, explaining what follows from the fact that it nevertheless degrades. He said the universe must run down, not the Earth, not the solar system, the whole thing. All the differences in temperature everywhere will eventually equalize. All the motion will eventually be converted into uniform warmth, and when that process is complete, the universe will be, in his phrase, condemned to a state of eternal rest. This was, as far as anybody can tell, the first time a human being had stood up in public and given a physical argument that everything ends. Not through the wrath of anything, not through collision or catastrophe, through arithmetic. I want to spend a moment on how that landed, because we are so used to this idea now that it takes some effort to feel it as new, and it was extremely new. The 1850s in Britain and Germany were not a period of pessimism. This was the high season of industrial confidence, of railways and telegraphs, and the sense that the natural world was steadily being brought to heel. The intellectual mood was progressive in the most literal sense. Things were understood to be getting better, and the trajectory was assumed to continue. Into that came a result from the most rigorous available science saying that the trajectory has a terminus, that the terminus is not optional, and that everything built along the way will eventually be at the same temperature as everything else. It hit hard, and it hit outside of physics. You can watch it move through the culture. It appears in the poetry, in the fiction, in the theology. There was a genuine crisis among religious thinkers about what it meant for a world that had been made deliberately to be running down by design. The physicist John Tyndall wrote about it. Later, at the end of the century, when H.G. Wells sends his time traveller forward in the time machine, what he finds at the end is not a war or a plague. It is a beach under a swollen, dull red sun, in a silence, with the last life on Earth barely moving. That image comes directly out of this physics. Wells had studied under Thomas Huxley. He knew exactly what he was writing. The Victorians called it the heat death of the universe, and the name has stuck, and the name is slightly misleading in a way that matters. It suggests death by heat, as though everything ends by being cooked. It is the opposite. It is death by thermal equalization. It is everything arriving at the same temperature, which for the universe as a whole is a very cold temperature indeed. The death is not caused by heat. The death is the heat having nowhere left to flow. And here is the thing that I find genuinely remarkable about this episode, and the reason I have spent this long on 1852 and 1854. They got there first. Before anybody knew the universe was expanding, before anybody knew there were other galaxies, before radioactivity, before the atom had been shown to have parts, before quantum mechanics, before relativity, before the age of the Earth was known to within a factor of 50, before anybody had the faintest idea what makes the sun shine. With none of that, working entirely from an argument about the efficiency of steam engines, two men correctly identified the direction in which everything is going. Almost everything they believed about the specifics turned out to be wrong. Thomson himself spent decades insisting the Sun could only be a few tens of millions of years old, because gravitational contraction was the only power source he could imagine. And he used that number to argue publicly against the geologists and against Darwin, and he was wrong. And he was wrong because nuclear fusion had not been discovered. The man who told the world it was running down was badly mistaken about how much time our own star had left, and mistaken in the direction of far too little. The specifics were wrong. The direction was right. That combination is worth remembering, because it is the same combination we are in now. But there was still something missing from all of this, and it is a strange absence to notice from the outside. Thomson and Helmholtz had described a process. They had said that energy dissipates, that differences flatten, that the universe runs down. What they did not have was a number. There was no quantity you could measure that told you how far along the process had got. There was no name for the thing that was increasing while all the usable energy decreased. You cannot really do physics with a tendency. You need something you can put on the left-hand side of an equation. Getting that number took another decade, and it took a man who had been circling the problem since the 1850s, who knew exactly what quantity he needed, who could write down its mathematical properties perfectly well, and who kept running into the same peculiar obstacle. The thing did not have a name, and he could not explain it to anybody until he built one. Rudolf Clausius had been working on this since 1850. He was a German physicist, careful, unhurried, not given to grand statements, and he had done something in that first year that Thomson had not quite managed. He had cleanly separated the two laws from each other and stated both. The first law, energy is conserved. The second law, heat does not spontaneously flow from a colder body to a hotter one. That second statement sounds almost too obvious to be a law of nature. Of course, heat does not flow from cold to hot. Everybody knows that. But look at what it forbids and you will see why it is not obvious at all. It does not say that the reverse flow is difficult, or that it requires a lot of energy. It says it does not happen on its own, ever, and that every apparent exception, every refrigerator and heat pump and air conditioner, works only by spending a larger quantity of usable energy elsewhere to force it, and always spends more than it moves. Clausius spent the following 15 years working out the mathematics of that statement, and the mathematics kept producing the same quantity. There was a thing that could be calculated for any system. It went up in every real process. It stayed the same only in idealized, perfectly reversible processes that do not actually exist. It never, under any circumstances, went down for an isolated system. He knew its properties precisely. He could compute it. He had been publishing about it for over a decade, and he had been calling it the transformation content of the body, which in German is Verwandlungsinhalt, a word that is accurate, unwieldy, and completely useless for communicating anything to anyone. Then, in the spring of 1865 in Zurich, he sat down to finish a paper. Picture the room. It is late April. A physicist in his early 40s is at a desk, working through the final section of a long and technical document about the mechanical theory of heat, the sort of paper that is read by perhaps a few dozen people in Europe. The lamp is lit. The pages are stacked. He has been at this particular subject for 15 years and he is close to done. And he decides that the thing needs a name. He goes into Greek and finds the word trope, meaning transformation, a turning. And then he does something that shows exactly what he thought he had. He deliberately shapes the new word so that it sounds like the word energy. He wants them heard as a pair. He wants anybody who encounters one to feel the shadow of the other. He says so explicitly in the paper. He has intentionally formed the word to be as similar as possible to the word energy, since the two quantities are so closely related in their physical meanings that a certain likeness in their names seemed to him appropriate. He calls it entropy. And then, at the end of a technical paper about heat engines, having just invented the word, he writes 2 sentences that have nothing technical about them whatsoever. 2 short declarative lines. He does not build up to them. He does not mark them as important. They simply arrive at the bottom of the page as though they were a summary of the day's work. The energy of the world is constant. The entropy of the world tends to a maximum. I want you to hold on to those 2 sentences, because we are going to come back to them at the very end of tonight, and by then they will mean something to you that they cannot possibly mean yet. But look at what he has done there. He has taken a result about the efficiency of machinery and stated it as a property of the world. Both sentences use the same word, die Welt, and both make a claim about everything. The first sentence is reassuring. Nothing is ever lost. The second sentence, once you understand it, cancels the comfort of the first entirely. Nothing is ever lost, and everything is nevertheless going one way, and the going is not optional. There is something almost unbearably ordinary about that scene. A man finishing a paper, tidying up, giving something a name because it was awkward not to have one. He was not announcing the fate of the universe. He was completing a piece of work, and the fate of the universe is what came out of the end of it. Now, having given you the word, I have to immediately warn you about it, because entropy is probably the most widely misunderstood term in all of physics, and the misunderstanding will get in the way of everything that follows if we do not clear it out now. You have almost certainly been told that entropy is disorder. That is the standard one-line definition. It appears in a great many textbooks, and it is close enough to be useful in some circumstances, and wrong often enough to be actively harmful. Here is why it fails. Disorder is a judgment made by a human being about how a thing looks. It is not a physical quantity. A teenager's bedroom is not, in any measurable thermodynamic sense, higher entropy than a tidy one. If you take a jar of black sand and a jar of white sand and shake them together, the result looks disordered to you, and its entropy has indeed gone up, so the intuition seems to be working. But then you look at a crystal forming in a cooling solution, going from a random scatter of dissolved molecules into a rigid, perfectly ordered lattice, which looks like order appearing out of nowhere, and the entropy of the universe went up during that process, not down. And the intuition breaks. Worse, and this is the one that matters most for tonight, the early universe was very nearly smooth. Hot gas spread out almost perfectly evenly, in every direction, to a precision of about 1 part in 100,000. That looks like the tidiest thing imaginable, and it was the lowest entropy state the universe has ever been in. Meanwhile, the universe today, full of stars and galaxies and structure and clumps, which looks far more organized, has enormously higher entropy. If entropy were disorder, the history of the universe would run backwards from what we observe. So put the word disorder away. It will not help you tonight. What entropy actually measures is something more precise and much stranger, and once you have it, a great deal of what has been confusing becomes almost obvious. It took another physicist to see it, and he saw it by asking a question that nobody working on steam engines would ever have thought to ask. He asked how many ways there are. Ludwig Boltzmann was Austrian, and he was working on something that most of his colleagues considered either unnecessary or slightly disreputable. He believed matter was made of atoms. That needs some explaining, because it sounds like believing the sky is blue. But in the 1870s, atoms were not established fact. They were a hypothesis, and a controversial one, and a significant faction of respectable European physics regarded them as an unnecessary crutch. Ernst Mach, who was enormously influential, took the view that since nobody had ever seen an atom, physics had no business assuming they existed. The thermodynamics of Clausius and Thomson worked perfectly well without them. Why invent invisible particles to explain something the equations already handled? Boltzmann's answer was that if you do assume atoms, something extraordinary happens. The second law of thermodynamics stops being a mysterious law that has to be imposed on nature and becomes an inevitable consequence of counting. Here is the idea, and I want to build it carefully, because it is the conceptual heart of tonight, and everything after this depends on it. Imagine a container of gas. From outside, all you can measure are a few bulk properties: the temperature, the pressure, the volume. That is the macroscopic state. It is what you see. But underneath that, the gas is made of an enormous number of individual molecules, each with its own position and its own velocity, all of them moving and colliding constantly. That full specification, every molecule's position and speed at a given instant, is the microscopic state. And the crucial point is that there are an unimaginable number of different microscopic states that all produce the same macroscopic state. You could swap two molecules' velocities, and the temperature and pressure would be identical. You could rearrange them 1 trillion different ways, and from outside nothing would look different at all. Boltzmann's insight was that entropy counts those arrangements. Entropy is a measure of how many distinct microscopic configurations are compatible with what you observe from outside. That is the whole definition. Not disorder, not mess, not decay, a count of possibilities. And once you have that, the second law becomes almost trivially obvious, which is the most satisfying thing about it. Ask yourself, if a system is constantly rearranging itself at random, through collisions, through the ordinary jostling of matter, where will it end up? it will end up in whichever macroscopic state corresponds to the largest number of microscopic arrangements, not because it is drawn there, not because anything pushes it, simply because there are more ways to be there. That is it. That is the second law. Systems evolve toward high-entropy states for the same reason that if you shake a box of coins, you get roughly half heads and half tails, not because the coins prefer it, but because there are astronomically more arrangements with a roughly even split than there are arrangements with all heads. Let me show you what this looks like, because I think it is one of the few things in physics that becomes genuinely visible if you slow it down enough. Put a glass of still water in front of you, clear, undisturbed, sitting on a table. Now let a single drop of dark ink fall into it. Watch what happens, but watch it slowly. The drop enters the surface and for a moment it holds together, a distinct dark shape suspended in the clear water. Then it begins to descend, trailing a thread behind it. The thread starts to curl. Fine tendrils reach outward from the main body, branching, thinning. The sharp boundary between ink and water softens and then disappears. Over minutes the dark shape loses its edges entirely, the colour spreading further and further, growing fainter as it goes, until the entire glass is a uniform, very pale grey, and there is no longer any part of it you could point to and call the ink. Now the question that matters. What pushed it? Nothing did. No force acted outward. There is no repulsion between ink molecules and water molecules driving them apart. There is no field, no pressure gradient, no current. Every single ink molecule is doing exactly what it was doing at the start, being knocked about at random by collisions with water molecules, moving in a direction determined by the last thing that hit it, with no preference for any direction whatsoever. Each individual molecule is as likely to move left as right, up as down, inward as outward, and yet the ink spreads outward every single time, in every glass of water, everywhere, without exception. The reason is that there is only one way to be a drop, and there are effectively infinite ways to be spread out. If you count the arrangements in which all the ink molecules are gathered in a small sphere near the top of the glass, you get a very large number. If you count the arrangements in which the ink molecules are distributed anywhere in the glass, you get a number so much larger that the first one rounds to 0 beside it. Random motion explores arrangements without preference, and so it finds the enormously more numerous ones. That is all that is happening. Now do something harder. Picture it running backwards. Picture the pale grey water slowly gathering colour in one region, the tendrils reforming out of nothing, drawing inward, thickening, the shape condensing, its edges sharpening, until a single dark drop of ink hangs in clear water, and then rises up through the surface and leaves the glass entirely. Here is what I want you to understand about that image. Nothing in the laws of physics forbids it. Not a single law. Every collision between an ink molecule and a water molecule is perfectly reversible. Run any individual collision backwards and it is still a legal collision, obeying every conservation law, indistinguishable from a normal one. If you filmed the microscopic behaviour of any small group of these molecules and played the film backwards, no physicist could tell which way round it was meant to go. At the level of the individual particles, there is no arrow of time at all. The unmixing is not forbidden. It is outnumbered. I want to make that concrete because outnumbered is doing a great deal of work in that sentence, and it is easy to hear it as a figure of speech. Take an ordinary deck of playing cards, 52 of them, fresh from the box in perfect order. Shuffle it thoroughly, and you will get some arrangement, and you will call that arrangement random, and if I asked you to shuffle it back into order, you would rightly say that this is not something shuffling does. But nothing about shuffling prevents it. Each individual shuffle is as likely to produce the ordered arrangement as any other specific arrangement. The reason it does not happen is that there are about 8 times 10 to the 67th possible orderings of a deck of cards, and only one of them is the one that came out of the box. That number, for 52 cards, is already larger than the number of atoms in our galaxy. If you shuffled a deck every second since the beginning of the universe, you would not have made a meaningful dent in the possibilities. Now scale up. A glass of water contains not 52 things, but something like 10 to the 25th molecules. The number of arrangements available to them is not merely larger than the card figure, it is larger in a way that makes the comparison useless. Every ordering of a deck of cards multiplied by every ordering of every deck of cards that could ever be printed is nothing against it. That is why the ink will not gather, not because gathering is illegal, because gathering is one arrangement and spreading is effectively all of them, and random motion does not aim. And the degree to which it is outnumbered is the thing that makes it feel like a law. For a quantity of liquid you could hold in your hand, the odds against a visible spontaneous unmixing are of a scale that has no comparison in ordinary life. We are not talking about 1 in a billion or 1 in a trillion. We are talking about numbers with more zeros in them than there are atoms in the observable universe. The event is not rare. It is not going to happen. Not in the age of the universe, not in 100 ages of the universe, not in any span of time you can construct. So the second law of thermodynamics is not a force, not a rule imposed from outside, not a tendency of nature toward decay. It is a statement about counting, and it is so lopsided that it behaves exactly like an absolute law, even though, strictly speaking, it is not one. That distinction is worth holding on to because it is not a technicality, and it produces one genuinely surprising consequence. Because the second law is statistical rather than absolute, it can be violated, in systems small enough that the counting is not overwhelming. This is a real, published, experimentally confirmed result called the fluctuation theorem, worked out by Dennis Evans and colleagues in 1993 and confirmed in the laboratory by Wang and colleagues in 2002. If you watch a single small bead suspended in water over intervals of a fraction of a second, you can measure it briefly running the wrong way, extracting energy from the thermal motion around it, entropy momentarily decreasing. It is real. It is measurable. It is also microscopic, lasts for fractions of a second, and averages away to nothing the moment you scale up. You cannot build anything on it. But I like that it exists, because it tells you the truth about the character of this law. It is not a commandment. It is a statistical certainty so overwhelming that it wears the costume of a commandment, and only in the smallest and briefest situations can you catch it out of uniform. Boltzmann worked all this out, and the equation that expresses it is engraved on his tombstone in the Vienna Central Cemetery. S equals K log W. Entropy equals a constant multiplied by the logarithm of the number of arrangements. There is a detail here that is usually got wrong and is worth correcting because it is a small injustice. Boltzmann never wrote that formula in that compact form, and he never introduced the constant K. The person who wrote it that way, and who first calculated the value of the constant, was Max Planck, around 1900 and 1901. The formula on Boltzmann's grave is Planck's rendering of Boltzmann's idea. Boltzmann himself did not live to see it carved there. He died in September of 1906 by his own hand, in a village near Trieste, after years of poor health and depression, and the long, grinding fight to have atoms taken seriously. Within a few years of his death, the atomic hypothesis he had spent his career defending was placed beyond reasonable doubt, in part by a young patent clerk in Bern, who had worked out that the random jitter of pollen grains in water was direct visible evidence of molecular collisions. So now you have the machinery. Entropy counts arrangements. Systems drift toward the states with the most arrangements. That drift is why heat flows from hot to cold and never back, why ink spreads and never gathers, why every process in the universe runs one way. But we still have not connected this back to the thing we started with. I told you at the beginning that the universe is running out of usable energy, while its total energy stays fixed. I have now told you what entropy is. What I have not yet done is show you exactly how those two facts are the same fact. That connection is the center of everything tonight, and it is where the picture you have been carrying since you were a child is going to come apart. The bridge between entropy and usable energy is a single expression, and I am going to give it to you in words rather than symbols, because the words are where the meaning lives. The free energy of a system equals its total energy minus its temperature multiplied by its entropy. 3 quantities. The total energy is everything the system has. The entropy is the count of arrangements we just spent the last part building, and the temperature multiplied by the entropy is a number that has the units of energy and represents something very specific. It is the portion of the total that is permanently unavailable to do work. Free energy is what is left after you subtract that. It is the part you can actually spend. So watch what happens as a process runs. The total energy on the left does not change because the first law does not permit it to change. But entropy increases because the second law does not permit it to do anything else. And because entropy has gone up, the subtracted term has got bigger, which means the free energy has got smaller. Nothing was lost. Something became unavailable. That is the entire mechanism. It is not complicated once you see it. Every process in the universe takes energy that was in a spendable form and moves some fraction of it into a form that can never be spent again, and the fraction is set by how much the entropy went up, and the entropy always goes up. The word for that fraction, historically, is dissipation. But I think a better everyday word is degradation, because nothing is dispersed in the sense of being scattered and potentially collectible. The energy is right there. It has simply been converted into a lower grade, and the conversion runs one way. Think of it like this. Suppose you had a very large sum of money, and every time you spent any of it, some fraction of your remaining balance was converted from cash into a form you could see on your statement, but could never withdraw. Your net worth would never fall. The number at the bottom would be exactly the same forever, and you would still eventually be unable to buy anything at all. That is the universe. Total energy, constant forever, spendable energy, declining monotonically, with every transaction moving a little more of the balance into the column you cannot touch. Now, I want to take the last step, the one this whole video has been walking toward, because there is a picture in your head that I have been letting you keep, and it is time to take it away. When I say the universe is running out of usable energy, you have almost certainly been imagining a supply, a quantity, something like a tank or a battery or a stockpile, a finite amount of good energy that was there at the start and has been drawn down ever since. It is a natural picture. It is the picture the phrase suggests, and it is the picture almost every popular account leaves you with. It is wrong, and the way it is wrong is the whole point. Usable energy is not a substance. There is no place where it is kept. You cannot isolate a region of space and say that this is where some of the universe's remaining usable energy is stored, because usable energy is not a property that a thing can have on its own. It only exists as a relationship between two things. Usable energy is a difference. Go back to the water wheel. A wheel does not turn because there is water. It turns because there is water above it and water below it. Put an identical wheel in a still lake containing 1,000 times as much water, and it will never move. The water is all there. The height difference is not. An engine does not run because there is heat. It runs because there is something hot and something cold, and it sits between them. Bring the cold side up to the temperature of the hot side, and the engine stops dead, with more total heat present in the system than there was before. A battery does not power your phone because it contains energy. It contains a chemical separation, two states that would rather be one state, and current flows for exactly as long as it takes to erase that separation. When the battery is flat, all the energy is still inside it. What has gone is the imbalance. Your body does not run on food because food contains energy. Food contains highly ordered, low-entropy chemical structures, and your body sits between those structures and the disordered warm carbon dioxide and water it exhales, and it takes its cut on the way through. Every single process that has ever done anything anywhere in the entire history of the universe has done it by standing in the middle of a difference and taking a share as the difference collapsed. And that changes what kind of problem this is. It changes it completely. A supply problem has a solution shaped like a search. If you are running low on something, there might be more somewhere else. You look further, you dig deeper, you get better at extraction, you find a new source. There is a whole grammar of hope attached to a supply problem, and every part of it depends on the thing being a substance that could exist somewhere you have not looked. A difference problem has no such grammar. You cannot go looking for more difference in the way you can go looking for more oil. Difference is not distributed unevenly across the universe such that some regions are rich in it and others poor. Difference is a structure, and structures can only be flattened, and every act of flattening is permanent unless you spend a larger structure to rebuild it. You cannot refill a flatness. I want you to feel the shape of that, because I think it is the moment where this stops being an interesting fact and becomes something else. You came into tonight most likely imagining a tank draining. That is frightening in a manageable way. Tanks can be refilled, or replaced, or rationed, and even if none of those work in practice, they work in imagination. And imagination is where most of our comfort about the future lives. What is actually happening is that a landscape is wearing flat. The universe began with hills and valleys, enormous differences, in temperature, in density, in the concentration of energy. Everything that has happened in 14 billion years has happened because something was rolling downhill. Stars formed because a gas cloud was denser in one place than another. Stars shine because their cores are hotter than their surfaces, and their surfaces are hotter than space. Planets have weather because one side faces a star and the other does not. Life exists because there is a 5,700-degree object in the sky and a 2.7-degree void behind it, and living things stand in the gap. And every one of those processes is erosion. Every hill that gets used gets slightly lower. There is no tectonics in this landscape, nothing pushing new mountains up. There is only the wearing down, and when it is done, the landscape will be perfectly level, and there will be exactly as much of it as there is now. That is the heat death. Not an empty universe. A universe that is completely full, every joule present, correct, and accounted for, arranged with perfect uniformity so that there is nowhere for anything to flow, and therefore nothing for anything to do. The richest possible universe, and the poorest, at the same time, for the same reason. There is something I've been aware of since we started talking about this, and I suspect you have been too, sitting just underneath the argument. If usable energy is a difference, and differences only flatten, then the total quantity of things that can ever happen in this universe was fixed at the beginning. Not the specific events, the total budget of eventness. Everything that has ever occurred and everything that ever will has been paid for out of an account that was funded once and receives no deposits. We are going to come back to that, and it is going to turn out to mean something different from what it seems to mean right now. But first I want to bring this out of cosmology entirely, because there is a way to see this happening that does not require any telescopes, or any imagination about the far future, or any trust in me at all. It is happening on the surface of your skin, at a measurable rate, and it has been happening every second of your life. Let me put you outside on a clear day. Stand somewhere open, close your eyes, and turn your face up toward the sun. You know the feeling. Warmth arriving on your skin, on your eyelids, immediate and specific, and if a cloud crosses it, you feel the loss within a second. Here is what is actually arriving. Photons. Particles of light that left the surface of the sun 8 minutes and 20 seconds ago, having taken, before that, somewhere between thousands and hundreds of thousands of years to work their way out from the core where they were made. That surface is at 5,772 Kelvin, and because the temperature of the source determines the energy of the photons it emits, the light landing on your face is high-grade light, concentrated, energetic, ordered in the specific sense that matters here. It is arriving from one small direction in the sky rather than from everywhere, and each packet carries a great deal of energy. The rate is about 1,361 watts, falling on every square meter held perpendicular to the beam out at Earth's distance. Across the whole disk of the planet that comes to roughly 1.74 times 10 to the 17th watts, 173,000 terawatts, continuously, day and night, for 4.5 billion years. About 30% of it is reflected straight back by clouds and ice and bright ground, leaving something over 120,000 terawatts actually absorbed. Now hold that number, and let me ask the question that undoes everything. Where is it all? 4.5 billion years of 120,000 terawatts is an amount of energy that beggars description. If any meaningful fraction of it had stayed here, the Earth would not be a planet. It would be a plasma. The oceans would have boiled off in the first few million years and the crust would have followed. So it did not stay. Almost none of it stayed. The Earth is not accumulating energy in any significant way. To a very good approximation, the planet radiates back into space every single day exactly as much energy as it receives. Turn your face up again and understand what is actually happening on your skin. Energy is landing on you, and at the same moment, energy is leaving you and leaving the ground and leaving the air, streaming outward in all directions into the dark. You're not a container being filled. You're a point in a flow, and the flow goes straight through. So if the books balance, if exactly as much energy leaves as arrives, then what on earth has the sun been doing for 4.5 billion years? What did all that light actually buy? Not energy. The energy came and went. What the sun supplies, and what everything alive on this planet has been living on since life began, is not energy at all. It is the difference in quality between what arrives and what leaves. The light that arrives comes from a 5,772 Kelvin surface. The infrared that leaves is radiated by an Earth whose effective temperature, seen from space, is about 255 Kelvin, which is roughly minus 18 degrees Celsius. Same quantity of energy, radically different grade. And this is where a number appears that I find genuinely one of the most quietly astonishing figures in all of physics, because it puts an exact count on the transaction. Since the energy in and the energy out are equal, but each outgoing photon carries far less energy than each incoming one, because photon energy scales with the temperature of whatever emitted it, the number of photons cannot be equal. Divide 5,772 by 255 and you get about 22. So for every single visible photon that arrives from the Sun, roughly 20 infrared photons leave the Earth. 20 out for one in, same joules. 20 times as many packets to carry them. That is entropy increasing made countable. One concentrated arrangement arriving, 20 diffuse arrangements departing, and the whole of terrestrial life, every plant, every animal, every forest, every city, every thought anyone has ever had, is funded by the gap between that one and that 20. Stay outside with your eyes closed for another moment, because there is a way to feel this that I think is worth having. The warmth on your face is arriving from one direction. That is the whole thing, right there. If you turn your head, you can find the edge of it. There is a specific place in the sky it comes from, occupying about half a degree, half the width of your smallest fingernail held at arm's length, and everything else in the sky above you is essentially cold. That is what low entropy looks like when it arrives, concentrated into a tiny angle, distinguishable from its surroundings, coming from somewhere rather than everywhere. And now feel the other half, which is harder because nothing in your body evolved to detect it. In every direction, from every square centimetre of you, infrared is leaving. It is going out from the backs of your hands and the top of your head and the ground under your feet, not from one direction but from all of them, into a sky that is at 2.7 Kelvin above absolute zero once you get past the atmosphere. There is no sensation attached to this. You have receptors for warmth arriving and none for warmth departing, which is a small accident of biology that hides half the transaction from you. But it is happening at every instant, and it is the larger half. The one small hot circle in the sky pays in, and the entire rest of the sky takes delivery, and the difference between those two facts is the only reason there is anything alive on this planet. This is what plants are doing. Photosynthesis is not a process for capturing energy, though that is how it is usually taught. It is a process for capturing order. A plant takes a small number of high-grade photons and uses them to build a chemical structure, a sugar molecule that holds its arrangement, and it pays for that construction by dumping a much larger quantity of low-grade heat into its surroundings. The plant becomes locally more ordered. The universe becomes less so by more than the plant gained. The books always balance in the wrong direction, and that is what makes it possible. Then something eats the plant and does the same trick again, one rung further down, keeping a fraction and degrading the rest, and something eats that. Every step of every food chain is another pass through the same machine, taking a cut from a difference on its way to being erased. The entire biosphere is an elaborate structure that has assembled itself in the path of a beam of low-entropy light, doing what a water wheel does in a stream, which means the answer to a question people have asked for a long time. How can life produce such extraordinary order in a universe that is supposed to be running down? Is not that life is an exception. Life is one of the most effective entropy-producing arrangements that has ever existed. A forest degrades sunlight far more thoroughly than bare rock does. Living things are not resisting the flattening. They are the fastest local route to it, and their internal order is a side effect of being extremely good at their actual job. And you, right now, are doing it at a rate of about 100 watts. That is roughly your resting output. A human body at rest radiates, conducts, and convects about 100 watts of heat into its surroundings, which is why a crowded room warms up and why you can feel someone standing close to you in the dark. Every one of those watts is energy that arrived in your body as a highly ordered chemical structure and is leaving as undifferentiated warmth. You're running a 100-watt conversion of order into heat, continuously, and you have never once stopped. And the moment you do stop, you will begin cooling to room temperature like any other object. So let me pull the pieces together, because we are about halfway through tonight, and I want to make sure the whole shape is clear before we push on into the strange part. We started with the observation that things run down, and found that no energy is ever lost when they do. We followed a French engineer to the discovery that every machine has a ceiling set by a temperature difference. We watched a Scot and a German extend that to the whole universe a century and a half ago, and we watched another German invent a word for the thing that increases. We took that word apart and found it was not disorder, but a count of arrangements, and that the second law is not a force, but the overwhelming arithmetic of there being more ways to be spread out than gathered. And then we found the bridge. Energy stays constant, entropy rises, and the product of temperature and entropy is the part of the total that has become permanently unspendable. And the conclusion we reached is that what is being spent is not a substance but a difference, not a tank draining, but a landscape wearing flat. And now we have found that landscape on your own skin. 20 photons out for everyone in, 100 watts of order becoming warmth. Not a distant cosmological process to be contemplated at a safe remove. The same process, at full speed, in you, tonight, whether or not you're thinking about it. Which brings me to the thing I've been carefully not saying, and it is the part where this stops being about the universe and gets personal in a way that people usually do not expect. If everything that happens has to be paid for out of a difference, and if you are a structure being maintained by a continuous flow of order through your body, then there is a question about you that has an exact thermodynamic answer. What is it costing to be you? In 1944, Erwin Schrödinger published a small book based on a series of lectures he had given in Dublin. It was called What is Life? He was a physicist writing about biology, which was unusual, and the book ended up being read by a generation of people who would go on to work out the structure of DNA, which is a large part of why it is remembered. In it he asked a question that seems simple and is not. Why does a living organism not simply come to equilibrium? Everything else does. Leave a hot cup of tea on a table and it becomes room temperature. Leave a wound-up spring and it eventually unwinds. Leave any physical system alone for long enough and it settles into the state with the most arrangements and stays there, doing nothing, forever. That state has a name in physics, equilibrium. And for an object like a human being, equilibrium is a very specific and very recognizable condition. Equilibrium for you is being the same temperature as the room, with your chemistry evenly mixed, with no gradients anywhere in your body. That is death, not metaphorically. Thermodynamic equilibrium with your surroundings is precisely and exactly what death is, described in the language of physics. A living body is a body that is not at equilibrium and is working continuously not to be. Schrödinger's answer to his own question was that an organism stays alive by continuously drawing order in from its environment and expelling disorder back out. His phrase for it was that an organism feeds on negative entropy, which is a slightly awkward construction he later apologized for and clarified. But the idea underneath it is exactly right, and it is the idea we have been building all night. You are not a container that stores energy. You are a pattern that is maintained by a flow. Think about what that means physically. Right now, inside you, there are concentration gradients being held against their own tendency to flatten. Sodium held at one concentration outside your cells and a different one inside, with pumps in every cell membrane working continuously to keep the difference. That gradient is what a nerve impulse is, a controlled local collapse of a difference that was expensively maintained, which is then immediately rebuilt so it can be collapsed again. Every thought you have is a cascade of tiny deliberate discharges of stored difference. There are proton gradients across the membranes inside your mitochondria, which are the direct descendants of free-living bacteria that were absorbed into our ancestors' cells around 1.5 billion years ago. Those gradients drive a molecular machine that physically rotates, a turbine a few nanometers across, spinning at hundreds of revolutions per second, and each rotation assembles the molecule that carries usable energy around your body. You have something in the order of a quadrillion of these turbines running inside you at this moment. They are water wheels. They are standing in a difference and taking a cut. Your body temperature is held about 20 degrees above the room you're in, which means heat is leaving you constantly, and you are constantly replacing it. Your blood is kept at a different chemical composition from the fluid around your cells. Your bones are being dissolved and rebuilt continuously. The proteins you're made of are being taken apart and reassembled on timescales of days. Almost none of the material in you is the material that was in you a decade ago. What has persisted is not substance, it is arrangement. You're a shape that matter passes through, held in place by a continuous expenditure, like a standing wave in a river or a flame that keeps its form, while everything constituting it is replaced from moment to moment, and every bit of that maintenance is paid for from the same account we have been discussing all night. The order you consume as food came, a few steps back, from sunlight. The disorder you produce goes out into the room as heat, and then eventually out into space as infrared, and then outward forever, contributing its share to the flattening. You are a temporary local decrease in entropy purchased with a much larger global increase. That is not a poetic description. It is a bookkeeping statement, and the numbers work out. There is something in this that I think is worth handling carefully rather than dramatically, because it is the sort of fact that could be delivered as horror, and I do not think horror is the honest response to it. Death, in this framework, is not an event that happens to you. It is what happens when the expenditure stops. Everything that had been held apart is allowed to mix. The gradients equalize. The temperature comes to match the room. The structure that was being continuously rebuilt is no longer rebuilt, and so the ordinary statistics of arrangements take over, and the matter that made up a person proceeds toward the enormously more numerous configurations that do not. Nothing is lost when this happens, in the strict physical sense. The energy is all still there. The atoms are all still there, every one of them, and they go on to be other things. What ends is the maintenance of an improbable arrangement against the odds. I said earlier that the second law is not a force. It is worth remembering that here. Nothing is attacking a living thing. There is no antagonist. There is only the fact that there are enormously more ways to be dispersed than to be a person, and staying a person requires continuous payment, and the payment comes out of a finite supply of difference that the universe made once, which is a strange thing to be told, and I think a stranger thing to notice about yourself while it is going on. You are, at this moment, an ongoing transaction, not the result of one. The transaction itself in progress, being funded by starlight that left a nuclear furnace and will end up as faint warmth spreading into a dark sky. So we have followed this from a steam engine to a glass of ink to the sunlight on your face to the inside of your own cells, and everywhere it is the same story. Differences being spent, never restored, always in the same direction. At which point the obvious question is no longer academic. It is not a curiosity anymore. It is a practical question about a situation you are personally inside of. Can anything be done? Because people have asked exactly that, and some of them were extremely clever, and one of them designed something so ingenious that it took physics 60 years to work out why it does not work. In 1867, James Clerk Maxwell wrote a letter to a colleague describing a thought experiment, and it was such a good thought experiment that it took until 1961 to fully dispose of it. Maxwell is one of the towering figures of physics, the man who unified electricity and magnetism and worked out that light is an electromagnetic wave, and he was not trying to break the second law. He was trying to demonstrate something about its character. He wanted to show that it was statistical rather than absolute, and to do that he constructed a scenario in which a being small enough to see individual molecules could apparently get around it. Here is the setup. Take a sealed container of gas at a single uniform temperature, divide it down the middle with a wall, and put one small door in the wall, and make the door frictionless so that opening and closing it costs no energy at all. Now, a gas at a uniform temperature is not a gas in which all the molecules move at the same speed. Temperature is an average. Within that average there is a wide distribution. Maxwell himself had worked out its shape, which is why it is called the Maxwell distribution. At any moment some molecules are moving much faster than average and some much slower. So station an intelligence at the door. Let it watch the molecules approaching from both sides. When a fast molecule comes from the left, it opens the door and lets it through to the right. When a slow molecule comes from the right, it opens the door and lets it through to the left. Fast ones accumulate on the right. Slow ones accumulate on the left. Let me put you in the room and let this run. Watch the door. Nothing about this looks like cheating. The demon is not pushing anything. It is not adding energy to the gas. The molecules arrive with whatever speed they already had and leave with the same speed. The door costs nothing to operate. All the demon is doing is choosing when to let things through, and choosing is not a force. But watch what happens to the container over time. The right side is getting warmer, the left side is getting colder. A temperature difference is growing out of a gas that started perfectly uniform, and a temperature difference, as we have spent all night establishing, is exactly the thing that you can run an engine on. So take the difference the demon has built and put a small engine between the two chambers. Extract work. Let the temperatures equalize again, then let the demon sort them apart once more and run the engine again, and again, forever. You have a machine that produces usable energy from a system at uniform temperature. You have found a way to reverse the flattening. You have refilled the landscape. Let that sit for a moment, because for around 60 years it genuinely sat, unresolved, in the middle of physics. This was not a crank proposal. This was Maxwell, and the argument is clean, and nobody could immediately say what was wrong with it. The obvious objections all fail. Perhaps the demon has to be very small, and small things are subject to random thermal motion. Make it larger and give it instruments. Perhaps the door leaks energy. Stipulate that it does not. Frictionless mechanisms are a standard idealization, and the argument is not supposed to hinge on engineering. Perhaps observing the molecules requires shining light on them, which costs energy. This one was pursued seriously, and it turns out you can construct versions where the observation cost is arbitrarily small, so it does not close the loophole either. The resolution, when it finally came from a completely unexpected direction. It did not come from thermodynamics, it came from thinking about information. The first real step was taken in 1929 by Leo Szilard, a Hungarian physicist who would later be one of the people who talked Einstein into writing to Roosevelt about the atomic bomb. Szilard simplified the demon down to a single molecule in a box, and showed that the crucial thing the demon does is not open the door. The crucial thing is that it must know which side the molecule is on. It has to acquire information, and Szilard showed that this acquisition is not thermodynamically free. But the argument was not fully closed until 1961, when a physicist named Rolf Landauer, working at IBM, published a paper called Irreversibility and Heat Generation in the Computing Process. He was not thinking about Maxwell at all. He was thinking about computers and about whether there is a fundamental minimum amount of energy that a computation must dissipate. His answer was subtle and turned out to be the key to everything. Computation itself, he found, can in principle be done with arbitrarily little energy, as long as it is reversible, as long as you could in principle run the steps backwards. But one specific operation is different. Erasing information is fundamentally irreversible, because it takes two possible prior states and maps them both onto one, and information about which one you started in is genuinely gone. And that operation has a price. Erasing a single bit of information requires dissipating at least a certain minimum quantity of heat into the environment. The Boltzmann constant multiplied by the temperature multiplied by the natural logarithm of 2. At room temperature, that is 2.87 times 10 to the minus 21 joules per bit. It is a fantastically small number, about 3 zeptojoules, about 1/100th of the energy in a single visible photon. It is roughly 1 billion times smaller than the energy a real transistor uses today. But it is not zero, and that is what matters. Now go back to the demon and watch its hands rather than the door. To sort a molecule, the demon must determine its speed. To act on that determination, it must hold it in memory, at least briefly, and the demon is a finite thing, so its memory is finite. Molecule after molecule, the record accumulates. Eventually the pages are full, and there is only one way to keep going. It has to erase. The moment it erases, it pays. 2.87 times 10 to the minus 21 joules, dumped as heat into the environment for every single bit cleared, and when you do the accounting properly, the work extracted from the temperature difference the demon built against the heat dissipated by the erasures the demon required, the erasure cost is always at least as large as the gain. Always. Not usually. Not in the versions we have checked. Structurally, by the same argument that gives the second law its force in the first place. The demon does not fail because it is not clever enough. It fails because information is physical, because memory is a physical arrangement of matter, and because clearing a memory is itself an entropy-increasing process that must be paid for. This was confirmed in the laboratory in 2012 by Beru and colleagues, published in Nature. They built a single-bit memory out of a microscopic bead held in a double-well optical trap, erased it, and measured the heat released. The measured value matched Landauer's limit. The bill is real, and it has been read off an instrument. Nature charges a fee, and the bill always comes. We first met that sentence as a complaint about steam engines, made by a French engineer in the 1820s. It has just come back with a number attached, in joules per bit. And now I want to turn it round and point it somewhere less comfortable. You are a physical system that acquires, stores, and erases information. That is not an analogy. Your brain is matter, arranged in configurations that encode states, and those configurations change. When you form a memory, something physical is written. When you forget, and you are forgetting almost everything continuously, which is a feature and not a fault, something physical is cleared, and clearing it costs at least 2.87 times 10 to the minus 21 joules per bit, dissipated as heat, into your skull, into the room, into the air, and eventually into the sky. Your thinking warms the room, not as a figure of speech. Your brain runs at around 20 watts, which is a great deal more than the Landauer minimum for what it does. Biology is nowhere near the fundamental limit, but the minimum is there underneath it, unavoidable, the same flaw that constrains every possible computer that could ever be built in this universe. Every thought you have ever had was paid for. Every memory you have lost was an erasure with a thermodynamic price. The consideration you're giving to this sentence right now is drawing on the same account that funds a burning star, in the same currency, subject to the same law, and there is no version of you that could think more efficiently than the flaw allows, because the flaw is not about biology or design. It is about what information is, and there is a detail in Landauer's result that makes this stranger rather than simpler, which is that the cost attaches specifically to forgetting. Acquiring information can, in principle, be done for nothing. Copying it can be done for nothing. Computing with it, transforming it, deriving conclusions from it, all of that can in principle be done reversibly, at arbitrarily low cost as long as you keep every intermediate step. The universe does not charge you for learning. It does not charge you for thinking. It charges you for letting go. The reason is that erasure is the one operation that genuinely destroys distinguishability. Two different prior states go in, and one state comes out, and the information about which one you started with is not hidden or moved. It is gone from the system, and the accounting requires it to appear somewhere, and where it appears is as heat in the surroundings. So a mind that never forgot anything would, in principle, be thermodynamically cheaper than one that does. And no such mind can exist, because memory is physical, and physical things are finite, and any finite system that keeps operating must eventually clear space. Forgetting is not a design flaw that better engineering would remove. It is the necessary consequence of being a bounded thing that continues, which means the price you pay for continuing to think is, precisely, the price of everything you have let go of in order to keep going. I find that oddly intimate rather than frightening. We have spent most of tonight looking outward at a universe running down at scales that do not care about us at all, and here the same law reaches all the way in, past the body, past the metabolism, into the most private thing there is, and says, this too, this costs. You're not observing the second law. You have never once been outside of it. So the cleverest attempt to cheat failed, and it failed for a reason that also applies to the person considering it. But the demon was only one attempt. There have been others, some of them still being attempted right now, and I promised you at the start that I would tell you why every single one of them fails. Before we get there is one more thing worth seeing, because we have talked a great deal about difference being spent and not much about where it goes when it is spent, and the answer to that turns out to be one of the strangest facts in cosmology. Almost all of it is in the dark. If entropy is a count of arrangements, and if it has been rising everywhere since the beginning, then it should be possible in principle to ask a very direct question. How much entropy is there in the observable universe right now, and where is it? In 2010, two Australian cosmologists, Chas Egan and Charles Lineweaver, published a paper in the Astrophysical Journal doing exactly that. They went through every significant contributor they could identify: starlight, the cosmic microwave background, neutrinos, interstellar gas, stars themselves, and black holes, and added up the budget. The total came to about 3 times 10 to the 104th in units of the Boltzmann constant. That is a 3 followed by 104 zeros, with substantial error bars in both directions, and it is not the interesting part of the result. The interesting part is the distribution. The cosmic microwave background, which is the leftover radiation from the early universe, and fills all of space in every direction, contributes about 10 to the 88th. The relic neutrinos contribute about 10 to the 89th. Stars, starlight, gas, dust, all of the things that we normally think of as being what the universe is made of, contribute amounts that are, on this scale, negligible. And black holes contribute essentially all of the rest, roughly 10 to the 104th, which means black holes hold about 15 orders of magnitude more entropy than everything else in the universe combined. Not 15% more, 15 orders of magnitude, a factor of 1,000 trillion. Every star that has ever shone, all the light they have ever emitted, all the gas in every galaxy, the entire cosmic background left over from the Big Bang, taken together, They are a rounding error against the entropy sitting inside black holes, and within that one class dominates: the supermassive black holes at the centres of galaxies, the ones with millions or billions of times the mass of the Sun. This is one of those results that sounds like a technicality and is actually telling you something profound about where you live. Here is why it happens. In 1972, Jacob Bekenstein proposed, and Stephen Hawking shortly afterward confirmed and quantified, that a black hole has an entropy, and that this entropy is proportional to the area of its event horizon, not its volume, its surface area. That is a genuinely peculiar result. Entropy for ordinary matter scales with the amount of stuff, which means with volume. Double the volume of a gas and you roughly double its entropy. But for a black hole, entropy scales with the area of the boundary, which means that as a black hole grows, its entropy grows faster than its mass. It goes as the mass squared. This is where the holographic principle comes from, and it remains one of the deepest unresolved puzzles in physics. Nobody has a fully accepted account of what microstates that entropy is actually counting. The practical consequence is that black holes are, by an enormous margin, the most entropy-dense objects that can exist. A black hole with the mass of the Sun has roughly 10 to the 20th times the entropy of the Sun itself. The same matter, reorganized, holding 100 billion times as many possible arrangements. And notice the strangeness of that. Externally, a black hole is the simplest object in the universe. It has no features. It is completely specified by 3 numbers: mass, charge, and angular momentum. And 2 of those are usually near zero. 2 black holes with the same mass and spin are not similar. They are identical in a way that no 2 atoms of the same element quite are. It is the plainest thing that exists, and it is the largest reservoir of entropy in the cosmos. That inversion is worth holding on to, because it demolishes the last remnant of the disorder intuition. The highest entropy objects in the universe are not the messy ones. They are the smooth ones, the featureless ones, the ones with nothing going on, which is precisely what you would expect once you understand entropy as counting arrangements rather than measuring mess. The more microscopic states are hidden behind a given macroscopic appearance, the higher the entropy, and a black hole hides more behind less than anything else can. So when I said earlier that the universe's supply of difference is being spent, this is the answer to the natural follow-up question. Where has the spent difference gone? Overwhelmingly, into black holes. They are the accounts into which the universe has been depositing its used-up capacity, and they now hold almost all of it. Let me take you forward and show you the end of this, briefly, because the schedule matters less than the mechanism, and I do not want to turn this into a tour of the far future. Star formation cannot continue indefinitely, because it requires gas, and gas gets locked into stellar remnants that do not give it back. The best estimates put the end of the star-forming era at around 10 to the 14th years, about 10,000 times the current age of the universe. And I want to flag that number because it is the first milestone in the sequence, and it is by far the shortest step. Everything after it is larger than everything before it, combined repeatedly. After the last stars, what remains is remnants, white dwarfs cooling toward black, neutron stars, and black holes, drifting in a universe with no new light in it. How long that phase lasts depends on whether protons decay, and here is an honest gap in the story. We do not know that they do. Grand unified theories predicted that they should, on timescales that experiments could reach. Super Kamiokande, a tank holding 50,000 tons of ultra-pure water, a kilometre under a mountain in Japan, has been watching for decades. It has seen nothing. The current limit says the proton's lifetime in the main predicted channel exceeds 2.4 times 10 to the 34th years. Every popular account of the far future assumes protons eventually decay, and the experimental evidence for that is at present 0. Whatever happens to ordinary matter, black holes have a slower and more certain fate. Because of Hawking radiation, they very gradually evaporate, though not yet, and this is a detail usually skipped. A black hole can only evaporate once the universe around it is colder than the hole itself, and a solar mass hole has a temperature of around 1/1000th of a Kelvin, far colder than today's background. It has to wait. Once evaporation begins, a hole with the mass of the Sun takes roughly 2 times 10 to the 67th years to finish. Evaporation time scales as the cube of the mass, so the giants at the centres of galaxies take around 10 to the 100th years. Let me put you at the end of that. There are no stars. There have not been for an unimaginable span. The sky is not dark in the way a night sky is dark because a night sky is crowded. It has the moon in it, and planets, and thousands of suns, and the faint collective glow of a galaxy. This is a place where the nearest object of any kind is beyond a horizon that nothing will ever cross, because the expansion of space has carried everything else out of reach permanently. In front of you is a black hole with 100 billion times the mass of the Sun, and it is, by an absurd margin, the brightest thing in the universe, which is to say, it is radiating at something like 10 to the minus 20 Kelvin, colder than anything you've ever encountered. Its glow so faint that calling it light is generous. Around it, the background of the universe has cooled below even that, toward a floor of about 10 to the minus 30 Kelvin. And this object, this featureless thing describable by 3 numbers, holds more entropy than every star that ever burned. It is where the difference went. Every temperature step, every gradient, every structure the universe ever built has been funneled into a handful of these, and now they are giving it back as the faintest radiation there has ever been, over 10 to the 100th years, until there is nothing left to give. Stay there a moment longer, because there is something about that scene worth noticing that is not obvious. It is not violent. Nothing in that picture is dramatic. There is no collapse, no explosion, no final catastrophe of the sort that endings are usually imagined to involve. The universe does not break. It does not tear or burn or fall in on itself. It simply arrives, over spans of time that make the current age of everything look like a rounding error, at a condition in which all the parts are the same as all the other parts, and there is nobody there to find it bleak, which is itself part of the description rather than a consolation. Bleakness requires a comparison, and comparison requires difference, and difference is precisely the thing that has run out. I also want to be honest that the schedule I have just walked through is the least certain thing I have told you tonight. The direction is settled. The mechanism is understood in detail and has been checked for 170 years. But the specific milestones, the eras, the boundaries, the evaporation times, are model-dependent extrapolations across spans of time that dwarf everything we have ever observed, and they rest on assumptions that are themselves unresolved. Whether protons decay, whether dark energy is truly constant or slowly changing, which recent survey data has raised genuine questions about. Whether our understanding of black hole evaporation survives contact with a full theory of quantum gravity, which we do not have. Change any of those and the timeline changes in some cases dramatically. What does not change is the direction. Every one of those uncertainties affects where the road ends and how long it takes. None of them affects which way the road runs. That is the destination. Everything still present, nothing anywhere different from anything else. So now we have the mechanism and the accounting and the schedule, which leaves the question I promised you at the very beginning and have been holding back all night. Is there any way out of this? Anything at all? People have tried. Let us go through what they tried, and then let me tell you the one reason all of it failed. Let us take the exits one at a time, honestly, giving each one its best case before closing it, and then let me show you that they all failed for the same reason, which is the answer I've been keeping back since the first minute of tonight. The first exit is the oldest, and it is the dream of a machine that runs forever. People have been building perpetual motion machines for at least 800 years. The earliest surviving designs come from 12th century India and 13th century Europe. The overbalanced wheel, with weights on hinged arms that swing out on the descending side to make it heavier there, which looks, in a drawing, as though it obviously must turn forever. It does not. Every version of it has been built, in wood, in iron, at every scale, and every version has slowed and stopped. The attempts never stopped either. Leonardo da Vinci sketched several and concluded they were impossible, and wrote rather sharply about the people who kept trying. In the 18th and 19th centuries there was a steady traffic of them, some sincere and some fraudulent, the most famous being Charles Redheffer, who exhibited a machine in Philadelphia in 1812, and drew paying crowds until an engineer noticed that the gear teeth were worn on the wrong side, meaning power was flowing into the machine rather than out. A hidden belt ran through a wall to an old man turning a crank in a back room. The pattern has held for 8 centuries with a success rate of exactly 0, and by the end of the 19th century the situation was so well understood that patent offices simply stopped engaging. The United States Patent Office has, for over a century, declined to examine perpetual motion claims without a working model delivered to the office, a requirement that exists for essentially no other class of invention, and exists here because the failure rate is 100% and always has been. There is a modern version of this, and it deserves to be taken seriously as a belief rather than mocked, because I think the reason people hold it is worth understanding. The claim is that working free energy devices have been invented and then suppressed, bought up, buried, or forcibly silenced by energy companies or governments. It circulates widely and it has a real emotional logic. If the rule is unbearable, then perhaps the rule is not a rule. Perhaps it is a policy. Policies have authors, and authors can be opposed. But the second law is not a policy and there is nobody to oppose. It is a counting result. The reason the overbalanced wheel does not turn forever is the same reason the ink does not gather itself back into a drop. Not because anyone forbids it, but because it is outnumbered by an amount that makes the word unlikely useless. There is no board of directors that could authorize an exception. There is nothing to suppress. The hidden belt through the wall is not a metaphor for a conspiracy. It is what is always, in the end, found. The second exit is more sophisticated and gets raised constantly, which is 0-point energy. And I want to be careful here, because the premise is completely real. Empty space genuinely does have a non-zero energy. The quantum vacuum is not nothing. It has fluctuations, and those fluctuations have measurable consequences. The Casimir effect is real. Place two uncharged metal plates extremely close together in a vacuum, and they are pushed together by a force arising from the vacuum structure. This has been measured to good precision. It is not fringe physics. So why is this not a fuel supply? Because of what the word ground state means. 0-point energy is the energy a system has in its lowest possible state, the energy that remains when you've removed everything removable. And extracting work, as we have spent all night establishing, requires a difference. It requires somewhere for something to fall to. A ground state is by definition the bottom. There is nothing underneath it. The Casimir effect illustrates this rather neatly. Yes, the plates come together, and yes, you can extract a small amount of work while they do. But then they are together, and the system is in its new lowest state, and it does nothing further. To run the cycle again, you have to pull the plates apart, which costs you at least what you gained. It is a spring, not a battery. It stores what you put in and returns a little less. The vacuum is not a reservoir of untapped fuel, it is the floor. The third exit we have already closed, but it belongs in the list, and it was the best one anybody ever built. Maxwell's demon, with its frictionless door and its perfect judgment, defeated by the fact that memory is physical and erasing it, costs 2.87 times 10 to the minus 21 joules a bit. 60 years of the sharpest minds in physics, and the loophole closed from a direction nobody expected. The fourth exit is the most beautiful, and I have a genuine fondness for it, because it does not try to break the law at all. It tries to outlive it. In 1979, Freeman Dyson published a paper in Reviews of Modern Physics called Time Without End, addressing a question almost nobody had asked with any rigor. Could life persist forever in a universe that is running down? His argument was ingenious. The problem with the far future is that free energy becomes scarce, and any process consumes it. But Dyson noticed that the rate of consumption is not fixed. If a civilization were to slow its metabolism as the universe cooled, thinking more slowly, running its processes at lower temperatures, and crucially hibernating for enormous stretches between periods of activity to radiate away waste heat, then the energy cost per thought would fall as the temperature fell, and the mathematics works out in a way that feels like a magic trick. A finite store of free energy, spent at an ever-decreasing rate, could support an infinite number of thoughts across an infinite span of time. Subjective experience would not end. It would simply be spread thinner and thinner, forever. Dyson took this seriously and worked out the details of hibernation cycles and radiator design. It requires two things. It requires that there be no lower limit to the energy cost of a thought, and it requires an open universe that cools indefinitely toward absolute zero. The discovery of the accelerating expansion of the universe in 1998 damaged both. If dark energy behaves as a cosmological constant, then the universe does not cool towards zero. It approaches a floor, the de Sitter temperature, around 10 to the minus 30 Kelvin, and stays there, warm, forever. A civilization cannot keep slowing down below the background it is sitting in. Worse, an accelerating universe has an event horizon around every observer, cutting each region off from everything beyond it, so the accessible supply of matter and energy is not merely finite, but small and shrinking. Dyson's eternal intelligence needed a universe that gets colder forever and stays connected. We appear to live in one that does neither. The fifth exit is a technicality that people raise with some excitement, and it is worth one paragraph. Poincaré recurrence. For a finite, isolated system, statistical mechanics says that after long enough, the system returns arbitrarily close to any state it has previously been in, so the heat death might not be permanent. Wait long enough, and things unflatten. The recurrence time for a universe is around 10 to the power of 10 to the power of 120 years, a number where the exponent has an exponent and where the notation itself gives up. Whether recurrence even applies to an expanding universe with a horizon is disputed, and it does not rescue anything. A random fluctuation back into a low-entropy state is not a continuation of anything. It does not preserve any structure, and the same reasoning implies that small fluctuations are overwhelmingly more common than large ones, which leads somewhere that most physicists treat as a sign that the reasoning has gone wrong rather than as a discovery. And the sixth exit is the most practical, and it is not really an exit. A sufficiently advanced civilization in the far future could extract energy from black holes, from the rotation of a spinning one, through what is called the Penrose process, or from the matter falling into one, at efficiencies far exceeding anything fusion can offer. This is real physics, and it would work. But it is not a way around the second law. It is simply finding the largest remaining gradient and standing in it, exactly as a water wheel does. It is the last big difference in the universe, and spending it is still spending. So there they are. 8 centuries of machines, the vacuum, the demon, eternal intelligence, recurrence, and the black holes. Every one of them failed, or in the last case succeeded only at delaying. And they all failed for the same reason. You cannot manufacture a difference without creating a larger sameness somewhere else. That is it. That is the whole answer, and I want to say it again in a slightly different way to make sure it lands, because everything tonight has been building toward this one sentence. Every scheme for getting free work out of the universe amounts to producing a gradient where there was none. And gradients can be produced. That is not forbidden. Your refrigerator produces one every second, making the inside colder than the room. But a refrigerator that is unplugged does nothing, and a refrigerator that is plugged in warms the kitchen by more than it cools the food. The gradient inside was bought with a larger gradient destroyed elsewhere, and there has never once been an exception, at any scale, in any experiment, in any circumstance. Usable energy is a difference and not a supply. That was the reframe in the middle of tonight, and here is where it pays. Because if it were a supply, the escapes would be search problems, and search problems can be solved by looking harder. But when the thing you need is a difference, every attempt to get more of it is an attempt to make one part of the universe unlike another, and doing that requires flattening a larger unevenness to power the operation. The books balance, and they balance in the wrong direction, every single time. There is no clever arrangement, there is no undiscovered configuration, there is not a machine we have failed to think of. The impossibility does not come from a lack of imagination, and it cannot be fixed by more of it, because it does not come from engineering at all. It comes from counting, and the counting does not care how ingenious the counter is. So the honest answer to the question I posed at the beginning is no. There is no way to stop it. Not slow it locally, which we do constantly. Not delay it, which any structure does simply by existing. Stop it, reverse it, or escape it? No. And I noticed that saying that plainly does not feel the way I expected it to feel, and I do not think it will feel the way you expected either. There is something in a clear answer that is easier to sit with than an open question, even when the answer is the one you did not want. But we're not finished, because there is a much better question hiding underneath the one we just answered, and almost nobody asks it. We have spent all night explaining why the universe is running down. Nobody has explained why it was ever wound up. Here is a question that sounds like wordplay and is not. Why does entropy increase? The obvious answer, the one we built carefully in the middle of tonight, is that high entropy states are overwhelmingly more numerous, so random evolution finds them, and that is correct. But watch what happens when you apply the same reasoning backwards in time. The laws of physics at the fundamental level are almost entirely time-symmetric. They do not distinguish between past and future. Take any microscopic process, a collision, an electromagnetic interaction, a particle decay. Film it. Run the film backwards, and what you see is still a legal process obeying every conservation law. There is no arrow anywhere in the basic equations. This is true of Newton's mechanics, of Maxwell's electromagnetism, of general relativity, and very nearly of quantum field theory. So the counting argument should work in both directions. If a system is in a given state now, and there are far more high-entropy states than low-entropy ones, then the same reasoning that says it will have higher entropy tomorrow also says it had higher entropy yesterday. The argument has no preferred direction, because the physics underneath it has none. But that is obviously catastrophically wrong. Yesterday had lower entropy, so did the day before. Run it back far enough, and you reach a universe with entropy so low that it is difficult to describe. The direction is real. We experience it constantly. We remember the past and not the future. We see eggs break and never unbreak. So where does the direction come from, if not from the laws? The answer, and it is the standard answer, and I want to be honest about how unsatisfying it is, the direction comes from the initial condition. The second law is not derived from the laws of physics alone. It requires one additional input, the assumption that the universe began in an extraordinarily low entropy state. Philosophers of physics call this the past hypothesis, and it is an assumption. It is put in by hand. Nothing in physics explains it, predicts it, or requires it. It is the thing you must add to time-symmetric laws to get the time-asymmetric world we actually live in. Every arrow of time you have ever experienced traces back to it. The reason you remember your childhood and not next Thursday is not a fact about memory or about brains. It is a fact about the initial conditions of the universe, transmitted through 14 billion years, arriving in your skull as the sensation that time has a direction. Cause precedes effect for the same reason. Coffee cools for the same reason. Everything that distinguishes before from after is downstream of a single unexplained fact about how things started. Now, how improbable was that starting state? This is where it gets genuinely difficult, and where our intuitions fail hardest. Think about the early universe, about 380,000 years after the Big Bang, when the cosmic microwave background was released. The universe was hot gas, spread out with extraordinary evenness. The temperature was the same in every direction to about 1 part in 100,000. We have measured this to great precision. It is the smoothest thing anybody has ever measured. And your instinct, if you have been following the counting argument, is to say that this must be a very high entropy state. Smooth and evenly mixed is exactly what a gas looks like at equilibrium. It looks like the glass of water after the ink has finished spreading. That instinct is wrong, and the reason it is wrong is one of the most counterintuitive results in cosmology. For ordinary gas in a box, ignoring gravity, evenly spread is indeed the highest entropy configuration. There are more ways to be spread out than clumped, exactly as we said with the ink. But once gravity is in the picture, the counting inverts. Gravity is universally attractive and has no opposite. Matter pulls on matter, always, with no repulsive version to balance it. And that means that for a self-gravitating system, the clumped configurations are the numerous ones, and the smooth configurations are the rare ones. Gravity makes clumping overwhelmingly probable. A gas cloud left alone under its own gravity does not stay smooth. It fragments and collapses, and the collapse releases energy, and the entropy goes up as it does. So for a universe full of matter, smooth is low entropy, clumpy is high entropy, and the maximally clumped state, everything collapsed into black holes, is the highest entropy state of all, which is exactly what the Egan and Lineweaver entropy budget showed us in the last part, which turns the entire history of the universe inside out. Every structure that has ever formed, the first stars condensing out of primordial hydrogen, galaxies assembling, planets accreting, the whole magnificent business of a featureless universe becoming a structured one, all of that is entropy increasing. It is not a defiance of the second law. It is not order emerging against the odds. It is the second law running its course. Gravity found a smooth distribution, which was rare, and has been busily converting it into clumps, which are common, and every star that has ever formed was a step toward the end. The universe did not start disordered and become organized. It started in a state of extreme improbability that happened to look smooth, and it has been falling toward its overwhelmingly likely clumped state ever since, and everything we find beautiful about it is scenery on the way down. Now, how rare is rare? Roger Penrose has attempted to put a number on the improbability of the initial state by estimating how much of the space of possible starting configurations would produce a universe like ours. His figure is 1 part in 10 to the power of 10 to the power of 123. I cannot make that number meaningful, and neither can anyone else, and I want to be honest about that rather than pretending otherwise. It is not a number you can build an analogy for. Consider. To write it out in ordinary digits, you would need 10 to the 123 zeros, and there are only around 10 to the 80th particles in the observable universe. You could not write this number down using every particle in existence as a digit. There is not enough universe to express how improbable the universe was, and that is where physics currently stands. The most confident thing we can say about the fate of everything rests on an initial condition that we cannot explain, cannot derive, and can only characterize as being of an improbability that exceeds the descriptive capacity of the thing it produced. There are attempts. There are always attempts, and they are worth knowing about even though none has settled the matter. Some cosmologists look to inflation, the theory that the early universe underwent a brief period of enormous expansion, hoping it might explain the smoothness, though critics point out that inflation itself requires a low entropy starting point to get going, which moves the problem rather than solving it. Penrose has proposed a hypothesis about the geometry of space-time at the beginning, constraining its initial curvature. Others have suggested that we should not expect an explanation at all, that initial conditions are simply brute facts, and asking why they were what they were is a category error. Nobody knows. That is the honest position, and I said at the start of tonight that I would be straight with you about where the certainty ends, so here it is. The direction is certain, the mechanism is understood in detail, the mathematics has been checked for 170 years, and the reason any of it is happening at all is a complete mystery, which leaves us in a peculiar position, and I have been walking us toward it all night without saying so. We have established that the universe is spending down a supply of difference. We have established that it cannot be replenished, that every attempt to replenish it fails for the same structural reason, and that the spending is what every event consists of. And we have now established that the supply exists because of something nobody can account for, that the whole account was funded once by an improbability so extreme it cannot be written down. You would think that all of this adds up to the bleakest possible picture, a finite, unrepeatable, unexplained endowment being spent continuously on its way to a permanent and featureless end. But I have been holding one thing back, and it is not a consolation, and it is not a loophole. It is simply the other half of the fact, and once you see it, everything we have discussed tonight turns over and looks like something else entirely. Try to imagine a universe at equilibrium, not the process of getting there, the finished state, everything at one temperature, no gradients anywhere, no differences of any kind between any region and any other. Now try to imagine something happening in it. You cannot, and the reason you cannot is not a failure of imagination. Nothing can happen there, not slowly, not occasionally, not in principle. Every event that has ever occurred anywhere consisted of something moving from a state of higher usable energy toward a state of lower usable energy, and in a universe with no differences there is nowhere for anything to move to. The energy is all still present. It simply has no capacity to do anything, and neither does anything made of it. And now notice what that means about the direction of time. We have spent all night talking about the second law as the thing that ends the story, but the second law is also the only reason there is a story. It is the only source of directionality in physics. The fundamental laws are time-symmetric. They do not distinguish past from future. The one and only thing in all of physics that says which way is forward is the increase of entropy, which means that at equilibrium there is not merely no activity. There is no before and after. There is no meaningful sense in which one moment follows another, because nothing distinguishes them. Time does not stop exactly. It stops mattering, which is worse and stranger. So run this backwards through everything we have discussed. The reason you can remember your childhood is the entropy gradient. Memory is a physical record, and records can only be made in a system that has somewhere to dump the entropy generated by making them, and only a universe running downhill provides that. The reason cause precedes effect is the entropy gradient. Without it, the notion of one event producing another has no direction and no meaning. The reason you can follow this sentence from its beginning to its end is the entropy gradient. Comprehension is a process, and processes need somewhere to run to. The reason your heart is beating is the entropy gradient. The reason the sun is shining, the reason there is chemistry, weather, music, conversation, and any structure anywhere more complicated than a uniform haze. Every single one of those is the flattening, not something happening despite it, something that consists of it. And this is the turn I've been holding back all night, the thing that makes this topic different from what its title promises. We are not fighting the current, we are made of it. I have used the word decline a great deal tonight, and it carries a connotation I now want to withdraw. Decline sounds like loss, like something being taken. But the flattening of the universe is not an antagonist that structure and life are struggling against. It is the mechanism by which structure and life occur. A star is not resisting entropy. A star is a large quantity of entropy being produced, and its light is the byproduct. You're not holding out against the second law, you are one of the more efficient routes by which it proceeds, and your thoughts are the byproduct. Nothing is happening to us. Something is happening as us, which reframes the finitude, and I want to be careful here, because there is a cheap version of this thought and a true one, and they sound similar. The cheap version says, things are precious because they are scarce, therefore enjoy them. That is fine as far as it goes, and it is the sort of thing that gets said about mortality generally, and it is not what I mean. The true version is stranger and more specific. The universe has a finite total capacity for events, not a finite amount of stuff. The stuff is conserved and permanent. A finite capacity for anything happening at all, established once by an initial condition nobody can explain, and drawn down by every event since. Which means that every occurrence, without exception, is being paid for out of an account that cannot be topped up and will not be refilled. This conversation costs something. Your attention to it is being funded by a fraction of the universe's remaining capacity for things to occur, converted into warmth that is spreading out from you right now and will keep spreading, thinner and fainter, until it is indistinguishable from the background. That is not a metaphor. It is the actual physical situation, and it has a magnitude in joules. We first met this idea as a complaint about steam engines. A young French officer, irritated that British engines were better, discovered that nature charges a fee on every transaction, and the bill always comes. It came back with a number attached at Landauer's desk, 2.87 times 10 to the minus 21 joules, per bit erased, no exceptions, no negotiation. And here at the end I think the bill is not what it looked like. It is not a penalty imposed on existence by an indifferent universe. It is the purchase price of existence. Nothing would happen if nothing were being spent. The fee is not something charged against the transaction. The fee is the transaction. Take it away, and there is no engine, no star, no thought, no moment following another moment. Which brings me back to two sentences written at the bottom of a page in Zurich in the spring of 1865 by a careful man finishing a technical paper who had just invented a word because the thing he was describing did not have one. The energy of the world is constant. The entropy of the world tends to a maximum. When we first heard those, they were opaque. A historical curiosity from the childhood of thermodynamics. Now listen to what they actually say. The first sentence is a promise of permanence. Nothing you have ever encountered will be destroyed. Every unit of energy in your body, in the light around you, in every object you have ever touched will exist forever, in some form, somewhere. Nothing is ever lost. That is a real and remarkable fact, and it is easy to miss how strange it is. The second sentence is the price of the first. Everything persists and nothing stays useful. The permanence is total, and so is the degradation, and they are the same process seen from two directions. Clausius did not draw out the implications. He simply wrote them down, one after the other, and finished his paper, and the two sentences have been sitting there ever since, quietly containing everything we have talked about tonight. The engines, the ink, the sunlight on your skin, the demon and its notebook, the black holes holding almost all of the entropy there is, the last faint radiation over 10 to the 100th years, and the improbability at the beginning that nobody can account for. So yes, the universe is slowly running out of usable energy, and there is no way to stop it. That is true, and everything we found tonight confirms it, and I am not going to soften it at the end. But it is running out because it was, once, improbably and inexplicably wound up, and it is running out slowly, through a sequence of events which include stars forming and worlds cooling and life arising, and at least on one small planet, matter arranging itself into a configuration capable of working out what is happening to it. That last part is not separate from the running down. That last part is what the running down looks like from the inside, at this particular moment, in this particular corner, while there is still enough difference left to support it. The account is finite and unrepeatable, and nobody knows where it came from. You are, right at this moment, spending some of it. That is what makes now expensive, and it is why nothing that is happening to you or around you, or in the quiet, ordinary business of being awake and warm and thinking on an evening, is small.